Hello everyone, in this video we're going to work through what I would describe as a very difficult physics problem. It involves climbing up a rope which is draped over a pulley. And so I'm going to start by setting up the problem, explaining what we're trying to find out, and then we'll get on with the working. I'll warn you that it's quite a long problem to solve. There are a lot of steps, but it's interesting. I would say it's quite rewarding to solve this, and there is an interesting result waiting for us at the end of all of this. So as illustrated in the diagram up at the top left, we have a rope, this thing over here, draped over a pulley. It's a smooth pulley, so we're ignoring any friction for this problem. So the parameters of the rope are that it has a total mass of lowercase m, and it has a linear density, in other words, mass per unit length of lambda. You could also formulate this problem in terms of linear density and length, or mass and length, but the solution comes out most naturally if we do it in terms of mass and linear density. So clinging on to one end of this rope is this person who I've represented as this colored in circle on the right hand side of the pulley. So this person has a mass of capital M, and initially this system is in equilibrium. So the person is just hanging there. There is a sufficient amount of rope draped over on the left of the pulley to keep that person hanging in equilibrium. So then suddenly the person is going to start climbing up the rope at a constant velocity relative to the rope itself. And the question is, for how long is the person actually moving upwards, right? Because if you think about it, as soon as this person starts climbing upwards, they're going to be pulling the rope downwards. And so although the relative velocity is always pointing in the upwards direction, eventually the rope is going to be moving down at a sufficiently fast rate that the person themselves will also be moving down as well. So the question is, for how long are they actually moving upwards? So I've just duplicated this diagram to illustrate that we have some initial equilibrium configuration at a time of 0, and then some other configuration a little bit later after a time t has passed. I'm just going to edit my diagram at time t a little bit to reflect how things will have changed. So our person will have climbed up a little bit, maybe they're now up there. In the process of climbing up, they will have dragged the rope down a little bit further on the right-hand side of the pulley. So the length of rope on the left-hand side will be a little bit shorter, and the length of rope on the right-hand side is going to be a little bit longer, like that. Let me see if I can make that rope line up. There we go. Okay, so we're going to define some parameters, some variables that we're going to be working with in this problem. I'm going to say the length of rope on the left-hand side of the pulley is L1, and the length of rope on the right-hand side of the pulley is L2. And I'm also going to introduce a variable y to tell us basically the height that the person has moved by compared with their starting position, right? So the starting position was over here, and I'm going to say the person has moved a distance, or a displacement, I should say, of y, which is a function of time. So let's start seeing what relationships we can come up with between the various parameters of this problem. So the first thing I'm going to do is come up with the relationship between L1 and L2, the lengths of rope on either side of the pulley. So what we're going to do is ignore the size of the pulley itself. So I'm going to say ignoring the size of the pulley, you would have a relationship that looks like L1 plus L2 is equal to something which I'm just going to call L, where L is the total length of the rope, right? If you wanted to include, to account for the finite size of the pulley, you could put a plus pi times radius on the right-hand side there. But just to keep the algebra a little bit less cluttered, we're going to ignore the size of the pulley for the purpose of this video. So we've got the length on the left plus the length of the right is approximately equal to the total length of the rope. So now let's try to come up with some equations of motion that will describe how our system evolves with time. The way to come up with equations of motion is to apply Newton's second law. So let's say Newton's second law. Let's apply Newton's second law to the person who's clinging onto the end of the rope to start with, right? So Newton's second law says resultant force is mass times acceleration. The mass of the person is this capital M. Their acceleration is the second time derivative of y. And we have to think a little bit carefully about the forces. The obvious force is the minus mg pulling them down, right? That's their weight. But there must be some force which causes them to move up. That's coming from basically the friction between their hands and the rope when they're climbing up. So we don't know anything about this frictional force for the moment. I'm just going to call this F, and note that the force that the rope is exerting on the person could depend on time. So I'm going to say f of t. Now, what about if we apply Newton's second law to the rope, which is a little bit trickier? We're going to consider the rope as just one single body. So the mass of the rope, which we defined originally, was lowercase m. The acceleration of the rope, you could either write it as L2 double dot or L1 double dot. Now it's going to be, I'm going to choose to do everything in terms of L2, the length on the right-hand side, instead of L1, because I think it just makes things a little bit more convenient, because that's the length of rope on the same side as the person. So I'm going to choose to write the acceleration of the rope as L2 double dot. And let's think about what forces are acting on the rope. Well, you have the weight of the right-hand part of the rope sort of pulling it down and tending to cause L2 to increase, right? So that force is a weight. The mass of the rope on the right-hand side is the linear density lambda times the length L2 multiplied by g. So that's the weight pulling downwards on the right-hand side. Then you have the weight pulling downwards on the left-hand side, which is tending to cause L2 to decrease and L1 to increase, right? So we're going to get a similar term, but its sign is going to be different. It's going to be lambda L1g. And then from Newton's third law, because we know the rope must be exerting this frictional force on the person to pull them up, the person must be exerting the same force on the rope, but in the opposite direction. And so because the person is moving up, they are going to be exerting a downwards force on the rope, on the right-hand side of the rope. And so that's causing L2 to tend to increase. So we're going to put our sign as plus, and that frictional force is F of t. It's the same force by Newton's third law. So let's try to eliminate some variables. Ideally, because we have an L2 double dot here, we would like our whole equation of motion to be only in terms of L2 instead of L1. So if you look at this L1 here, you can take your L1 plus L2 equals L equation up at the top there, use that to eliminate L1. So if I do that, in the process I can factor out this common lambda g, so we get lambda g, and you end up with 2 L2 minus L, just by substituting L1 as L minus L2. And then you've got your plus f of t at the end. Okay, and then just to summarize the equation of motion that we get from this, so we have lowercase m L2 double dot is, we've got our first term from those brackets, 2 lambda g L2. The second term is minus lambda gl, but lambda times L is just the total mass of the rope. So that's just, we can write it as minus lowercase m g, and then we've got our frictional force, F of t at the end. So now we've come up with a pair of equations of motion involving y and L2. The variable we're more interested in is y, because the question is asking about how the person is moving. So ideally, we'd like to eliminate this L2 from the second equation of motion there. So we're going to need a couple more equations that are going to help us eliminate some of these variables. So I'll tell you where you can get some more useful relations from. It's the fact that I specified at the beginning that the relative velocity between the person and the rope is a constant. So I'm going to say, from the fact that we have a constant, I'll say vrel, for the relative velocity between the person and the rope, that implies that y dot, which is the velocity of the person upwards, plus L2 dot, which is the velocity downwards of the right-hand side part of the rope, that is going to be equal to this vrel quantity, which is a constant, right? And so this is sort of directly translating into equation form the fact that the relative velocity is a constant, but we can do some more useful things with this. In particular, you can differentiate it with respect to time to find a relationship between y double dot and L double dot, which is useful because those appear in the equations of motion, right? So if we differentiate it, we get y double dot plus L2 double dot is just 0, because differentiating a constant gives you 0. You could also go the opposite way, and you could integrate it and get y plus L2 is relative velocity times time plus some constant which I'm going to call k. Now the reason why this integrated equation here is useful is because it involves L2, and so we could use that to substitute for this L2 in the second equation of motion up there. However, now we have yet another unknown quantity, which is this constant of integration k over here. If we had some initial conditions, then we could fix that, and in fact we do. We know that the initial configuration of the system is that it's in equilibrium, right? So there's no motion initially. That will allow us to fix the constant k. So let's consider the balance of forces before the person starts actually climbing up. So I'm going to say from the initial equilibrium condition, in other words, when time t is equal to 0, then what do we get? Well, essentially the weight pulling down on the left should be equal to the weight pulling down on the right, and hence the total mass on the left has to be equal to the total mass on the right, right? So we can say total mass on the left is lambda L1, total mass on the right is lambda L2 plus the mass of the person, capital M. And notice that this specifically applies when t equals 0. This is not a general relation, but only when t is 0. We could then go back to our equation at the very top. L1 plus L2 is the total length L, and use that to eliminate L1, which is the length that we don't really care about, right? So if we do a little bit of substitution, you will get lambda multiplied by L minus L2 on the left-hand side. That's still equal to lambda L2 plus capital M. And then note that lambda times L is the total mass of the rope, so that's just lowercase m. I'm going to take the lambda L2 and put that on the other side so that we get 2 lambda L2 plus capital M, and then you finally arrive at the result that your initial value of L2 is lowercase m minus capital M, all divided by 2 lambda. And at this point, I'll just point out one implication of this equation is that for this whole situation to work, your small m has to actually be larger than your capital M. Otherwise, you'll have a negative length. So the rope has to actually be heavier than the person in order for this to work. Now, why is this useful? Well, go back to this equation, y plus L2 equals v rel t plus k, and note that when t equals 0, y is 0 by definition. And so if you consider the situation when t is 0, you just get k equals L2, which means this expression that we've just found here, m minus m over 2 lambda, is just the value of k, right? So then specifically, when we plug that k back into that equation up there, we end up with y plus L2 is equal to v rel times t plus all of that stuff, m minus m over 2 lambda, and then the initial conditions are satisfied. At this point, I should probably start labeling some of the equations that we're going to use later, because we're building up a lot of conditions here. So I'm going to call the first equation of motion up here equation 1. I'm going to call the second equation of motion number 2. I'm going to call this condition on the accelerations equation 3. I'm going to call this condition on y and L2 equation 4, so that we can refer to those later on. Now let's see if we can get to an equation of motion that only involves, well, where the only unknown quantity is y, because that's ultimately what we're interested in this problem. First thing we want to eliminate is this f of t, this frictional force between the person and the rope, which we don't really know anything about. Fortunately, you can eliminate f of t by taking equation 2 and substituting it into equation 1. So if we do that, your left-hand side will still be my double dot. Your right-hand side, so I'm taking all of equation 2 and substituting f of t from there. Your f of t is going to become m L2 double dot minus 2 lambda g L2 plus lowercase mg. So all of that stuff there, that's your f of t from equation 2, and then you have to subtract off big mg from the end there. So now all we've got to do is eliminate this L2 double dot and this L2 because we want everything to be only in terms of y. So the way to do that is using equations 3 and 4. I'm going to use both of those at the same time. So left-hand side, well, you've got my double dot on the left-hand side. From equation 3 up here, you know that L2 double dot is just minus y double dot. Right, so if I say that this L2 double dot here is minus y double dot, and then I move that onto the left-hand side, I'm going to get small m plus big M times y double dot on my left-hand side. So that takes care of this m L2 double dot term. Now, how else can I tidy up the right-hand side? Well, you can factor this term, factor a g out of those two terms at the end. So you've got small m minus big M times g from those final two terms. Then I've got minus 2 lambda g, at this point, we use our equation 4, which is this one over here, to substitute for that L2. And so L2 is equal to VREL times T plus that term m minus m over 2 lambda, and then minus y. Now I'm going to need to clear off some of these equations from the top of the screen, so you may want to pause and just have a look over any steps that you weren't sure of there, and then we'll move on. So now what we have as a result of all that work is a second order differential equation for y, which we ultimately want to solve. Before we can solve it, we just want to tidy things up a little bit. So some terms conveniently cancel. You've got this m minus mg here. Notice that the m minus m over 2 lambda, which is inside the bracketed term, when you expand the brackets, you get this extra factor of 2 lambda g. And so it turns out that the term at the start of that right-hand side cancels with that middle term in the brackets. So that's quite nice. If we do that, we get m plus m times y double dot is just, I'm going to also flip the minus signs around and get 2 lambda g times y minus relative velocity times t. And then we want to put this into a more standard form for a second order differential equation. I'm going to put the y terms on one side and the other terms on the other side. So we are going to get m plus m, divide everything by 2 lambda g. That's the coefficient of y double dot. I'm going to move my y term over to the left hand side, so minus y. And then on the right hand side, we're just left with minus vrel times t. So now we are able to use some standard methods for solving second order ODEs. In particular, we are going to split our solution y as a function of t into two parts, is the complementary function and the particular integral. I'm not going to review all of this stuff in a huge amount of detail, but as a quick recap, the complementary function is what you get if you were to set the right hand side as 0, and the particular integral is an extra little bit of the solution that accounts for the fact that you have this sort of forcing term on the right hand side. So let's find the complementary function first. The standard thing to do to find your complementary function for an equation like this is to try an exponential solution, because you're looking for a function such that you differentiate it twice, add it to some multiple, subtract off some multiple of the original function, and you're supposed to get 0. And exponential functions can satisfy that type of equation. So we're going to try a solution of the form where the complementary function is proportional to e to the alpha t, where alpha is a currently unknown coefficient. So the nice thing about this is when you differentiate that twice, you just pull down a factor of alpha squared, right? So if I take that, substitute it into our differential equation, but set the right-hand side equals 0 because it's the complementary function, you get m plus m over 2 lambda g times alpha squared minus 1 is equal to 0. And I've sort of implicitly divided everything by e to the alpha t because it's not 0, so you can divide through by that. So then we can just solve this equation for alpha. That's fairly straightforward to do. You get alpha is plus or minus the square root of 2 lambda g divided by small m plus big M. And for convenience, I'm going to say that this is plus or minus beta, right? Where beta is basically this entire square root term, just for our notational convenience. So what this means is because there's two different values of alpha, your general complementary function is going to be a linear combination of those two exponentials. So you've got some coefficient a times e to the positive beta t plus some other coefficient b times e to the minus beta t. Now I'm going to use a little trick here, which is actually to rewrite this in using a different basis of functions, because again, it's just going to make our algebra a little bit more convenient later on. So this is a linear combination of exponentials. If you're familiar with hyperbolic sine and cosine functions, you'll know that those are also linear combinations of exponentials, e to the beta t and e to the minus beta t. So you can equivalently write this as a linear combination of hyperbolic trig functions. So I'm going to say, so alternatively, I'm sort of redefining my coefficients a and b. Now I'm going to say y complementary function is a times the hyperbolic cosine of beta t plus b times the hyperbolic sine of beta t. Again, you could work through this whole problem using exponentials and end up at the same final result, but switching to hyperbolic trig functions at this stage will make things a little bit easier. Now, how do we find the particular integral? Well, you look at the form of the forcing term in your differential equation. Here, the forcing term is minus vrel t. That is a linear function of time. And so you basically guess the solution. You say, let's guess that our particular integral is going to be the most general linear function possible. I'm going to say gamma t plus delta because we've already used alpha and beta. And you just take this and substitute it into your differential equation. So the second derivative of this is just 0, so the y double dot term doesn't contribute anything. Putting that back into your differential equation, you'll get minus gamma t minus delta, because you had a minus y on the left-hand side. That's supposed to be minus vrel t. And by comparing coefficients of t, you can conclude that gamma is simply vrel, and delta has to be 0 because there's no constant term in our sort of forcing function. So then we know our particular integral, we know a complementary function, we're now in a position to add them together and write down our sort of general solution for y. It's going to be a hyperbolic cos of beta t plus b hyperbolic sine of beta t plus that particular integral, which is just vrel times t. So here's the general solution to that equation of motion for y that we had. So now we've got to fix the constants a and b using some boundary conditions. So the easy boundary condition is that, I guess I should say initial conditions rather than boundary conditions. The easy initial condition is that y of 0, when t is 0, y is just 0. Again, by definition, that's just how I've defined the y coordinate. If you plug that in to your general solution on the line above, because hyperbolic cos of 0 is 1, and hyperbolic sine of 0 is 0, you'll simply find the coefficient a has to be 0, right? So the hyperbolic cos part disappears. We need a second initial condition, which is going to come from y dot of 0. However, at the moment, we don't know what that is, but we can work it out, or at least work it out in terms of this fixed constant parameter vrel. So I'm going to draw a little diagram, a small diagram over here, which shows what's going on just as the person starts moving. So the person is going to be moving upwards. Let's say that their initial velocity in, I guess what we'd call the lab frame, is just u. Now, as soon as they start moving upwards, the rope has to start moving downwards, again, from Newton's third law. So let's call the initial velocity, downwards velocity of the rope, let's call that u dash, right? Now, we know that the relative velocity, vrel, is just u plus u dash, right? Because that's u, because they're moving towards each other, you just add the velocities to get the relative velocity. The other condition that relates u and u dash, you can either think of it as a kind of conservation of momentum, or in terms of Newton's third law. But the idea is that the person in the rope exert equal and opposite impulses on each other. And so the person's mass m times their initial velocity u has to be the rope's mass, small m, times the rope's initial velocity, u dash. So we've got these two conditions that relate u and u dash. So if we substitute the second one into the first one, you'll find that your relative velocity vrel is u times 1 plus this mass ratio, big M over small m. And then ultimately what we want is actually this u value, right? That's the initial upwards velocity of the person in the lab frame, which is just y dot, right, at time 0. So this is the thing we're interested in. If we rearrange that and do a little bit of algebra, we'll find that u is equal to small m over the sum of the masses times this relative velocity parameter, right? So what that means is we now have this initial condition, which is that y dot of 0 is small m over m plus m times vrel. So let's go back to our general solution at the top of the screen. We're going to have to differentiate it once. If you differentiate b as a hyperbolic sine of beta t, you just pull out the factor of beta and your hyperbolic sine turns into a hyperbolic cos. So you get beta b, but then hyperbolic cos of 0 is just 1. So that first term is just beta b. When you differentiate vrel t, you just get vrel because that's a constant. So plus vrel. And that is all supposed to be equal to this term which we've derived. So I'm just going to copy and paste that over here. Okay, so that's from our initial condition and from differentiating our general solution. If you rearrange this to make b the subject, you will find that it's minus 1 over beta times now capital M over small m plus big M times VREL. So now you know that A is 0 and B is this combination of parameters over here. We're now in a position to go back, plug both of those into our general solution, and you'll find that the specific solution here is, well, you can factor out a VREL, because that's sort of a prefactor in all of your terms in y. You get this t from the end of the expression up there, and you get minus 1 over beta times big M over the sum of the masses times the hyperbolic sine of beta times t. So there is our solution for y and how it varies as a function of time. Now we're almost but not quite done, because what the question was originally asking was for how long is the person actually moving upwards. I guess you can see at a glance from the functional form of y as a function of time that there will be some time after t equals 0 when y is 0 again, right? So that sort of automatically tells you that y must have gone up and then come back to 0. But in order to actually find how long they're moving upwards for, you're going to have to differentiate, find y dot. So if we do that, we get this VREL factor. T differentiates to 1. This second term will become big M over M plus M times hyperbolic cos of beta t, right? This 1 over beta factor cancels when we differentiate. And so when the person has just reached their maximum height, they've instantaneously stopped moving. So y dot has to be 0 there. If we require this bracketed term to be 0, we deduce that hyperbolic cos of beta t has to be the sum of the masses divided by capital M. Then what you can do is go back to your beta factor up here in terms of all of the parameters of the problem, and then solve this equation for t by taking inverse hyperbolic cos and then dividing by beta. And you arrive at your final result, which is t is the square root of m plus m over 2 lambda g times inverse hyperbolic cos of m plus big M all over big M. Now for me, the interesting thing about this result is that it's completely independent of the relative velocity, that VREL parameter that I introduced to help us solve the problem, which is why I didn't give that as one of the parameters of the problem initially. So it's maybe a little bit surprising at first that it doesn't have any dependence on how fast the person is climbing, but it does make some amount of intuitive sense when you think about it, because the faster the person is trying to climb, the faster they'll also be causing the rope to fall below them, right? And as it turns out, these two effects basically cancel each other out. And so regardless of how quickly the person is trying to climb up, they can only ever climb up for this certain amount of time. So anyway, if you've made it this far, then well done. I hope it's been interesting and a little bit of a challenge. And I hope to see you again soon.